So this is kind of an opportunity for me. I asked a number of my students to come to this. Raise your hand if you're one of my students. Because we've been working really hard on some stuff together, and it just seemed like this was an opportunity to talk about some of the stuff that we're doing that's in progress. So not everything you see is going to be finished, but you'll see our work. And from what Andy's told me about this general crowd, you kind of want to see the stuff the way it's really happening. So is that right? Right. We're not here to see, like, the latest James Cameron movie, right? This is like stuff happening. And one of the things that I decided I would do is then sort of dig down and think about how did I come to where I am in this stuff. So it all started for me with Marx. Actually, not that Marx. Actually, not that Marx either. I actually ended up starting on the course where I am today because of the Marx Plastics Company, which made these. And these are little plastic dinosaurs. How many people had little plastic dinosaurs when they were a kid? So the amazing thing when you're a kid is, like, you're 2, 3, 6 years old, you pick up this hunk of plastic, and there's the Brontosaurus, and there's the T-Rex, and you just spend all day making stories with them. And when you're a little kid, you never stop making stories. We have this amazing ability as kids to just take pieces of plastic and make stories, and somehow we lose a lot of that. And I realize that a lot of what I've done is try to kind of recapture some of that. Like, it's almost like the research is a prosthetic to allow you the superpower of being a kid or something like that. So when I was a kid, I would take my little plastic dinosaurs. Can people see this okay? Okay. I'd take them on journeys, and they'd have little chats and conversations, do dances. My favorite, actually, of all the dinosaurs, I did have a favorite. My favorite was the Brontosaurus. All of them actually had little words embossed on the plastic that said what they were. They all came labeled. And the reason that I loved the Brontosaurus when I was a kid was all the dinosaurs, as you probably know, are extinct. But at some point during my childhood, they realized that the Brontosaurus never actually existed. It was a mistake. It was like the head of an Allosaurus and the body of something else or something. And so in some sense, it was more extinct than the others. And I found that to be just so poetic that I thought somebody needs to love the Brontosaurus, which actually leads to the next thing, which is when I think about some of the other influences of my work, one of the biggest influences of my work is actually now exactly a century old. Can anybody name that character other than Cynthia?
Gertie?
Yes, it's Gertie the dinosaur. Just because my friend Cynthia knows absolutely everything about everything, so it's unfair. Yes, Gertie the dinosaur was animated by Winsor McCay in 1914. And in fact, not only did he animate Gertie, he did 10,000 individual drawings to make this beautiful dinosaur come to life. It was incredibly painstaking. She had character, she had emotion, but he would do something that actually people stopped doing for some reason. He would give live performances where he would draw Gertie, and then of course the film would start playing, and people didn't really know about animation. It's like, oh my God, the drawing's coming to life, it's incredible. And then he would do things like feed Gertie an apple. He'd palm the apple, so it's like he'd hand the apple to Gertie, and then the apple would disappear from his hand, and Gertie would eat the apple and walk off very happily. And it was really wonderful, because it was magic. And now at some point we have this idea now that animation is something you passively receive, but this was really exciting that this happened a century ago. And then other childhood influences that to me were similar were, all right, name that story. Well, people must know this. Harold, that's right. That's Crockett Johnson's 1955 children's book, Harold and the Purple Crayon. Harold had this purple crayon, and he would use it to make his world. Whatever he needed, he wanted to make the moon, he would draw the moon. He wanted to escape through a window, he would draw a window. And I just, as a kid, just thought this was the most incredible thing. And then skipping forward a little to 1963, I want to show you my favorite childhood device. It's the three-dimensional blackboard, or the 3D BB, which was invented by Mr. Whoopi, the friend of Tennessee Tuxedo, and his, who is a penguin, and his best friend, the walrus, named, anyone know who? The name of the walrus, can you remember? Chumley. And they would go on these little adventures. And hopefully my connection to the internet will work. And so every time they got into a scrape, at some point, Mr. Whoopi would explain to them how some technology worked. So kids were actually doing stealth learning in 1963.
But there's still something I don't understand, Mr. Whoopi.
Well, what's that, my boy?
I looked real close, and I didn't see any picture going across the room between the camera and the TV set.
But of course you didn't. There wasn't any picture, just electromagnetic waves which are invisible.
But then how?
How does it get to be a picture again? Well, let's go back to the 3D TV.
Three-dimensional blackboard,
Inside
folks.
every TV set, there's a big tube. You call it a picture tube, but the correct name is cathode ray tube. It takes the waves from the transmitter and turns them back into electrons. In the back of this tube, there's an electron gun which shoots the electrons at the front of the tube.
That's Chumley.
The front of the tube is coated with a special chemical which lights up when the electrons hit it. And this is what makes the picture.
I get it. The orthicon tube turns the picture into electrons, and the cathode ray tube turns the electrons back into the picture.
Precisely, my boy.
So cool. I love that this penguin knew that it was called an orthicon tube. A little bit of breaking the fourth wall there. Yeah, so there was actually a guy named Joe Harris who came up with this show, and he knew that he was more likely to get his show on TV if he made it educational. So he put that in there. And that man who looks and sounds like the Wizard of Oz, Frank Morgan, is actually not voiced by the guy who did the Wizard and Wizard of Oz. It's actually voiced by Larry Storch, who also played Agarn in F Troop, just so you know. He's magnificent with voices. For those of you who know or even care about such things. So, so then, of course, as I got a little older, I got other influences. Name that movie? Fantasia, right? That's, of course, Chernobog, the wonderful devil, mountain devil from Night on the Bald Mountain sequence. And he was just such a beautiful, beautiful character. He was animated by Bill Teitler, one of the great Disney animators, who actually, to get those amazing devil-like movements, studied Bela Lugosi in Dracula, and then copied the character and his movements from Dracula. So there was a lot of cross currents going on here. There are two movies here. The one on the right is obscure, but the one on the left is Forbidden Planet from 1957, and that is Dr. Morbius, played by Walter Pidgeon, who, using the power of the Krell, the sort of the extinct super duper race that they discover on this planet, is visualizing in a 3D floating in space display his daughter. There is, I mean, actually, this is actually a retelling of The Tempest. I highly recommend it. That guy on the right is Leslie Nielsen, who is when he was young and thin and not funny yet, and he's basically in love with the daughter, and there's a whole triangle between the dad and the daughter, and she's like the Miranda figure and all this, for those of you who know your Shakespeare. What was interesting about this is exactly 20 years later, another movie directed by George Lucas not only took the idea of the beautiful young woman floating in space without even needing a screen, it's some sort of unknown holographic thing, he actually copied the exact camera shot. So I think this was back when George Lucas was stealing from good movies, and I think it was much better. I don't know what happened to him after that. But this concept that you can have something floating in space without a screen is a really interesting concept in pop culture. Back when all this stuff was happening, what people cared about in both of these movies actually were the robots, because we were in industrial America, so it was like post-World War America, and everybody cared about robots because robots were the symbol of the future. We can make mechanical versions of ourselves. Actually, an interesting thing about both these movies is now, if you watch a science fiction movie, the symbol of the future is not the robot anymore, because we've shifted, actually the late 80s, we shifted from an industrial economy to an information economy. What's the impossible symbol of the future that every sci-fi movie has to have that actually can't exist in today's world? Can anyone think what it is? You keep seeing it in every movie.
Time travel?
No, the one in every movie, as soon as I say it, you realize it, is something has to be floating in space without a screen. So in Iron Man, in Hunger Games, and it's just the rules. You're not allowed, there's a contract in Hollywood, you're not allowed to make a sci-fi movie without something floating in space without a screen. And actually, we have no idea how to do it. But it's in every, it's like, oh yeah, there's Robert Downey Jr. He's going like this, and going like this. We're just supposed to accept it. And I think it's because the sort of the magic screenless iPad is now our kind of shortcut signifier of, oh, it's the future. So these things always reveal like where we are in our culture. So Tron, the real Tron, not whatever that was a really good movie, but it also, everything in it, all the computer graphics in it, looked like they came from machines. And so my personal history was that I reacted against the cold, hard look of Tron to start making things that would seem to have more life in them. I wanted things that felt like they could be in our world and not just look like they came out of a CAD program. Because these are beautiful, and they were, a guy named Chris Wedge, who then went to found Blue Sky, made Ice Age and other great movies, did animate these beautifully, but they still look like machines. So I started making some procedural textures to be able to make things that looked like they could be in the real world, like marble or like water or like fur. And so I started really appreciating this notion of proceduralism. Unfortunately, I did it too early because there wasn't, there were no hardware accelerators and NVIDIA boards yet, unfortunately. But I started then trying to make a lot of things I could. And when I got to NYU, using procedural methods. If you go to my homepage, there's hundreds of things where I just like little visual essays where I just try something out and say, oh, let me see, what would it be like if I made something like this? So they're essays in code instead of essays in words. And I'm going to show you a few of them because they relate to one of the two themes of this talk. And I'll just telegraph. The two themes of this talk are immersing ourselves in make-believe worlds and saying, okay, how do we make our world extend so that it's still a world that we inhabit, but it's one that has things we could never get in our boring old humdrum everyday world. And how do we make characters come to life? Like, I want to interact with the Chernobog character. I want that purple crayon to really work. I want Gertie the dinosaur not to just be a trick, but I want Gertie the dinosaur to actually respond to me in my world. So here's some experiments I've done through the years. The first ones you're going to see are in Java, because until last summer I was just doing everything in Java, and then at some point Larry Ellison decided that Java on the client side is boring, and so he stopped supporting it. And so now I've switched over to JavaScript and WebGL. But so for years I did, how many people have programmed in Java? Like client-side Java, it's really wonderful, but they're not being nice about it anymore. So this is my little demo. And this is a little character. It was the simplest character I could make. I try to basically follow the rules of simple Disney animators, which is make the simplest character I could make, but make it purely procedural. So this character, when you just tell it simple things, like now it starts to walk, or it can be like really arrogant, or it can be jumping, or you can make it hunt, and or it can be very sad. It's a sad character like that. Or you can answer questions, no, or yes. Or, maybe it's got hot feet. Or it could run really fast. Or hop on one foot. And so what's going on here that's so interesting is that in the course of about 20 seconds ago, 20 seconds after about 5 minutes of battling with Java, we sort of created this sort of sense of who this character is, even though it's an extremely, extremely simple character. And what's fascinating to me about this whole, let me actually run these things just straight. I'm going to run these demos straight because if I try to go into doing it the other way, who knows what it'll do to me. So again, I started trying to play around with this notion of interactive characters, that sort of you respond to them, they respond to you. And one of the things to keep in mind when I'm doing this is that everything I'm doing is a kind of puppetry. These characters already have a lot of personality and life in them, and I'm not so much animating them as I am directing them, the way a director directs a movie. So just to explain to you what's going on with some of this, if I hit the U key, you can see there, very small, he's unhappy. If I hit H, he gets happy. If I hit A, he goes ah. You see, or eh. so we can now make different things happen with the character. So for example, let's start a timeline going and make a little story with this little fish character. So the fish character, time starts going, and we start a ball bouncing, and it makes him really happy. He sees a ball bouncing, and he's like, hey, the ball's bouncing. That's really cool. But then we go there, and he's like, oh, that was bouncing. Wait a second, I didn't make the ball bounce, did I? Let's make the ball bounce. See, he was living in the world of my mind. So that was weird. You messed up my story. All right, okay, now he's happy. All right, and so then we go there, and it doesn't work, and he's like unhappy. And then he goes back to this one, he goes back to that one, and he's very confused. And then, of course, we make this one bounce, and then he goes, yay, that's really cool. Ooh. And then, ooh. And then, of course, we go back there, and then maybe we give him something really wonderful. We make it like totally huge, and then he's like, hey, this is really great. So there's like a little story that, now the interesting thing about this story is that as I'm making this story, I'm actually also communicating with the server, and that little script is actually on a server that other people can share. In fact, you can go afterwards, and the mistake that I made when I first did this, was I had him be really happy that the ball was bouncing, but I didn't have the ball bouncing. So I can actually go and fix that. I can say, oh, let's fix the movie, so now the ball is actually bouncing. So if we go back and we start the movie going, then now he's like now it's working correctly. Like I've edited the movie. And people can simultaneously edit this. So one of the things that's interesting to me is to try to push character intelligence just high enough that they can be actors who can take direction. And then you can start having different kinds of storytelling. And then the hope is that then if you are going to put these characters eventually into a shared virtual world, some sort of immersive world or three-dimensional visualization, that the AI, the artificial intelligence, to have them make decisions in response to us doesn't have to be as hard because they already know how to act. All we need to do is give them the little bits of directing. So we're sort of moving halfway toward solving the problem of how do they respond to us by making them not joints and limbs and inverse kinematics and stuff, but actually intentionality and knowing how to hit their marks and look at things and express emotion. So I'm going to try to go back into the talk now, and actually maybe I'll show you one more thing before I do that. Let's see, where is it? I'm going to show one more thing while I'm here. So at some point I started trying, I'm really into Jane Austen. How many people here like Jane Austen? So in fact, my favorite book is Pride and Prejudice. And so after reading Pride and Prejudice, I was in an airplane and I put together a little demo. And these characters basically are supposed to be an acting troupe that one day will act out Pride and Prejudice, because they remind me of the sort of official upper class twits from Regency England. They sort of move around, and and then there's one character, and of course everybody can be staring at that character. Social approbation. And they're not very smart, but very, very full of themselves. And then we could even make it immersive, eventually, hopefully. We can make it so that you're part of the story or something. But so then when I started doing some stuff with trying to integrate this into stories, and I started trying to integrate, I'll show you some work in progress of trying to make interactive scripts using these characters. So I took these characters and I put them into a little system. It was like a little sort of, and Adam Gaslin there worked with me on this, where they're basically, this is a story that these little characters are acting out, but they're taking direction. So they're not animated there, and I'll show you what's going on behind the scenes in a moment. So of course, it's the classic love triangle. It's very sad. But now we can change the story. We can say, instead of calling the story poor Wilma, we'll call it poor Fred. So now we're going to tell the story again, and they're switched places. So Wilma is shy now, but Fred is persistent. But Wilma likes Ethel. And of course, Fred is now sad. So the reason we can do this, they're hitting their marks, they're going to the right places, is that we're using actually a high-level script. In fact, we can look at the script actually as the actors are variables. In fact, we can go behind the scenes and we can actually get a little crazier. We can say, I want us now start visualizing what will this be like when we live in that future world where these characters are in our world. So this is a bit of a fake, but I'm going to just change the background to true. So when it runs, it'll load a background. And now they're on like a desktop. It's a desk place I was staying this summer in Vancouver. And they're acting out the same story. But the idea is now they're acting out the story right in front of you. Now, we haven't implemented that yet. But by visualizing it and saying, what would it look like if these characters acted out right in front of my telephone and my Apple? Apple the fruit, for those of you who haven't made that association for a while. Then that gives us a sense of what would we do? How would we change the content? Would we, for example, change it so that they respond to, like, if you pick up the phone, they scatter, and then when you go back, they sort of resume their little story again, like, oh, it's the humans again. So it's like thought experiments, throwing these things together and thinking, what would it be like? So that gives you a sense of some of that. Now, I wanted to go to this picture because this is a picture that I love. This is a picture that was from when I was a kid, or actually a little before I was a kid. There was this movement that was really popular basically up until, I would say probably up until the Kennedy assassination. People actually thought the future was going to be a better place. I know those of you who are younger don't believe that's possible because you can't imagine such a world, but then we entered Vietnam and everybody started, distrusting the government, and Nixon got in, and it's like, I don't even want to go there. But there was a time before that when technology was good, and wow, the future is great, and plastics don't even kill you, and it was a very different world, and people were making pictures like this. And now, of course, there's a movement that's sort of a nostalgia movement, looking back on that long lost time. Now the future, basically, Ridley Scott decided the future would look what it looked like in Blade Runner. It's like everything's dark and dystopian, and everyone wears black, and you're all going to die anyway. So what's the point? But it wasn't like that, really. And so there's now this movement called retro future, where people are trying to imagine like that sort of rosy, positive, hey, remember when things were going to be great? And so I still kind of have some, come on, what happened to my mouse? There you go. I still have some of these ideas. Let's go back to then some of the things people have done to try to go into virtual worlds, thinking they were going to go into a better place. Like this was their idea. So this was, I believe this rig actually was one of the experiments, if I'm not incorrect, of VPL, which is Jaron Lanier's company, back around 1986, when it was really hot. There were no LCDs, since you actually had to have little video cubes, just like the ones that Tennessee Tuxedo was talking about. And there was the data glove, and you had to wear this heavy thing. But this was actually wearable with lots of wires trailing. So it was pretty darn good for the fact that it was a quarter of a century ago. And so people kept trying different form factors as the technology advanced. People kept trying to make more and more sleek, let's just go into some world, virtual thing. This one didn't work out so well. So once in a while, they would run the wrong direction, but then they would autocorrect. But then you had people like Thad Starner, and can anyone name this person? Steve Mann, that's right. So the two of them, or each of them, if you ask them, each of them actually did this before the other one. They will assure you that that's a fact. But they were actually both starting out in the early 90s, basically, trying to be cyborgs, which means that what that meant was they're wearing all the time. They're going through their daily lives, constantly doing this. And of course, now Thad is part of the team that is bringing you Google Glass. Except people have been talking about, and the engineering isn't insane. I mean, at first they thought it was, but now it's kind of within the realm of plausibility, the magic contact lens. You put the contact lens in, and something happens, and there are even some prototypes that do some of this, and you see whatever it is you want to see. And then there's the audio, and then there's the tracking, and the 6th degree of freedom with 0 latency, and all that, and it's like, it's not crazy now. Now it's being seen as an engineering problem. So somehow you have some crazy optics that go right on your eye, and so it has to be diffractive optics, holographic, because there's no place for an optical system there. But actually, the technology sort of exists. I mean, this is an actual industrial object that's in common use. This is a diffractive mirror that takes a laser. And if you shine a laser from the right angle, it will just act like a mirror or like a prism and will just redirect it. And you could put that at a nanoscale on a contact lens, and it would just send the light into your eye. So there isn't to your retina. So it's not completely insane to talk about some of these form factors. It just is a lot of engineering and power and other things to be done. And eventually, and people are already doing work on this, eventually they're going to be able to do direct simulation right into your brain. There are already technologies now that can optically excite your neurons using infrared right through your skull. I don't know if anybody is nervous about that. The thing that worries me about that is that actually they can do that, and they can also do the opposite thing. So the beginning technologies are there for being able to excite your neurons, make you see things, blah, 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 and also figure out what's going on inside of you without actually ever having to do any surgery. And of course, since we know that this is a society where privacy is very respected by the government and corporations, I think we have nothing to worry about. But if we didn't live in such a society, maybe you guys should be thinking about that. Oop, what happened? Did it freeze? Did the computer freeze again? I think every time I touch this thing, the computer freezes. Come on. What happened? My mouse is not moving, is it? Oh, there you go. OK. So let's talk again about Star Wars. Star Wars is just one of a set of visions of what it would be like if we could see whatever we want. And it's my sense, given the physics of it, that that's going to happen sooner because of stuff we wear and then eventually implants than it is because we're going to find some law of physics that allows us to make stuff happen right out in space itself. Now, I mean, oh, implants, oh my God, that's crazy. Except, you know, we have implants. You know, we have LASIKs, we have pacemakers. Everything is completely insane and scary in science fiction until it's just ordinary and nobody thinks about it anymore. And I am completely convinced that 25 years from now, when the artificial retina inside your eye is better than the natural retina, every parent will demand that their child have it so that they will be able to compete with the other kids. And that's the way the world is going to go, because that's the way the world always goes. I mean, if you had told people from a few hundred years ago that we'd be hurtling through the air, 30,000 feet in the air, and going to California in a few hours, they would obviously lock you up. But that's the world we live in now. So, so I think the issues are not, they're engineering issues, but they're being worked on right now by the large corporations. And if you, as soon as you know anything about it, you have to sign NDAs, and then you're not allowed to tell anybody. But it's a question of what we do with it. And of course, you know, Star Wars was fun because they had this whole vision, like there's Endor floating in space. You know, all these people are seeing this planet in virtual reality just floating right there from all points of view holographically at the same time using some unknown kind of technology. And yet at the same time, if you really look in the background, you see these old-fashioned CRT displays. And you ask, like, so if they had a world where you could just make stuff float in the air magically, why did they old-fashioned CRT displays? And there is actually a reason for that. And the reason for that is in 1977, if people went to a movie theater and you didn't show them old-fashioned CRT displays, they'd be very confused. So it was actually all about telling a story. Oh, it doesn't make any sense. And then there's, you know, other movies that are all about fashion. That sort of have this idea that, yes, we actually are just inside of a complete, you know, we're lying in some vat somewhere, and, you know, something's plugged into the back of our heads, and then eventually we wake up and we're Keanu Reeves, and we haven't moved in years, and yet we're totally buff, which doesn't make any sense. And he'd probably really look like one of the characters from WALL-E, you know, which then people wouldn't go see the movie. So there's, this is an interesting thing that I found. It's kind of obscure. It's an ad from 1965 for something that's a combination telephone and television. And they try to push this, when you think about it, they try to push this almost a half a century ago, which was very forward-looking of it, and people didn't want it. People were like, hey, look, this is my telephone and this is my television. They have nothing to do with each other. I don't want to mix them. And of course, what the problem was that there were certain layers of intervening technology and culture that weren't in place. And now we mix our telephone and our television all the time, and we don't think about it. And the key was that they both had to become portable and things we carry around with us in our pockets and wireless. But the concept was right, but they were half a century, almost half a century too early. So the reason that I say this is that a lot of the things that we talk about that might seem nuts are nuts because we're just coming at them too early. And it's important for us to talk about these things, not just because they could be exciting, but also because we don't want the bad things to happen, like the invasions of privacy, et cetera, et cetera. And we need to be thinking about these things before they're just, you know, you belong to Mark Zuckerberg. Whatever, and his minions. So I like this picture because it sort of tells me that little kids will just accept anything. You know, even little kids and monks, they'll just like, okay, sure. I'm wearing my 3D glasses, I'm looking at this thing, this is the world I live in, it's fine. And so it often is young people who kind of push the envelope because they don't care. They're like, right, I didn't grow up in that other world, I'm going to try another thing. And I think that we should be all embracing that mindset of try something and see if it works. There's a really nice book from 2006. That's not very good as a novel, but it's really good as an idea piece. Has anybody read Rainbow's End? I highly recommend you read it. I don't like it as a book. Clearly, he didn't care about his characters or plot development or anything. But he's positing, Werner Vinge's positing a world about 25 or 30 years in the future where everybody's wearing. And what we mean by that is that you pop in the two contact lenses and you see whatever it is you want to see, but you're still in the same room with other people. So we're in this room together, but you might see it as a Western theme, and I might see the same room as Hello Kitty, you know. And then maybe there's somebody from California floating right there in the air between us, and we're having a conversation between them based on our available bandwidth. And he really works through what's the relationship between the virtual, the tactile, and all these kinds of things. And it's a fascinating read. And so this picture really inspires me because it's so ordinary and prosaic. I like this is, you know, this is sort of a visualization of some future reality in which there's a gumball machine that looks like it's on the street. But it's not a gumball machine, it's a virtual gumball machine. Now, you might argue, well, that's silly, there's no gumball machine there. You know, it's just somebody stuck a computer graphic. But if everybody sees the gumball machine, and it's there with absolutely rock solid, no jiggling, from the right perspective and the right lighting, from everybody's perspective, it becomes part of our shared reality. This may seem a little weird, but if you go back, if you think back to like people from 7,000 years ago, you know, before what we consider any form of modern technology, and if you presented them with an object like this, plastic, and it's clear, and it's got straws, and we forget the computer, just something like this, or the fabrics of our clothing, they would tell you that such an object can't exist. Clearly, such an object is not possible in our reality. So as soon as technology enables something, it exists, and then we have to decide what to do with it. So these are going to be real things. They're going to be ordinary things, and we have to think what we want to do with them. They're going to be part of our art. We did a project about 2 years ago where we asked the question, what would it be like if I could just explain something to you and we had some unknown future technology where I could just like draw stuff in the air? And Jonathan worked on that. And another grad student, Murphy, who's now got his PhD, yay, worked on that. And I'm going to show you a little snippet from that. And before I show it to you, I want to explain the ground rules. We made a rule that some of the stuff they're doing is real, absolute correct tracking of objects. Some of it is fake, but the rule is that absolutely everything must be happening in camera in real time, no editing. So when you're going to watch this and you're going to see cut to another camera, the moment when it cuts to another camera, the system automatically figured out, oh, we're cutting to another camera. The virtual reality is now being seen with another camera. We have to actually change that. So it's all happening in real time with no post-production. So let's skip up to, so Xiao is from MIT, but I'm going to, in the interest of time, I'm going to skip past her thing, and I'm going to go up to Murphy's thing.
Topographic maps are a kind of map that shows elevation. Let me show you how.
So this is not post-production. This is all happening while you're watching.
let's see this map in 3D. And let's make it bigger. And let's make it steeper, and also add more contour lines, which correspond to the steepness. Now let's crush it back down, and bring it back to a topographic map, and add color, which can show the absolute height, which contour lines alone can't do. Bring it back down. Now let's rotate it towards you.
So what is he seeing?
Now let's fly over the region.
I'll tell you in a moment.
And see how the colors and the contour lines change together to show the shape of the region. Cool, huh?
He's seeing in this version. Who asked the question? I couldn't see. Okay, he's seeing actually a display just below where the camera is that's giving him a sense of like what's going on. And there's a certain amount of him being able to see things, and a certain amount of him just saying, "I know something's there. I'm going to look at it."
So it's like a weather map, like
yeah,
before.
yeah.
That's green screen, though. That's all.
Yeah. So what we're trying to do is tie that together with real-time tracking, so that people could improvise. So the vector of our research is to go from it's the thing that they on the click track, that you knew was going to happen, to the I just think I want to talk about this thing now, and it just occurred to me, let me make something happen in the air and let's discuss it. So that's what we're trying to do. But so some of our research is different parts of our research are different places along that vector. And now, one of the things that's crucial for making this happen is your really, really good hand tracking. Now, Jonathan, I'm going to embarrass now, Jonathan Thompson is been working with Murphy on, I think it's the best hand tracking technique that's out there. Instead of, what turns out to be really, really hard to track people's hands. It's much more difficult than tracking a human body. The Microsoft Kinect, which they're using, or they're using the equivalent of it, is good at big things and very, very bad at small things. And yet, heroically, they're trying to use it with small things where the depth image is incredibly noisy. And the way that they're doing it, roughly speaking, is they're training a machine learning algorithm, artificial neural net algorithm, on many, many different examples of hand poses. And then once that training is done, then now the trained up system, just as we sort of know what hands look like, and so we can recognize them later, when it sees even a really noisy depth image, it sort of figures out, oh, okay, I get what the hand pose is, and reconstructs it. So the first thing they do, forgive me for explaining your work, is this is Jonathan, and he's got an algorithm that's basically segmented automatically out his hand. So the software just is, you're looking at the depth image from essentially a Kinect, it's a prime sense. Now he's using multiple depth cameras together from different directions, and that's not his hand. That's a computer graphic hand that he got off the internet and then conformed to have the same hand and finger shapes as his. So that's a synthetic hand, and he's using it to train a machine learning algorithm. And what he's doing is he's establishing, these are now the correspondences between the depth image and what he's getting from the joints of the artificial hand. So he spends hours computing and then gets those correspondences. Now in real time, he's taking a single depth image from just a commercial depth camera and working out where all those spots are, because his algorithm is trained to understand that depth image and figure out where the spots are. And then the final step is he basically fits like a little mechanical robot hand behind the scenes. Once he has those spots and he knows the distances, he uses what some of you will know as inverse kinematics to say, okay, let's put a computer graphic hand on top of that. And then, and now you're seeing it's trying to fit the synthetic hand to this. But what's really exciting about this is just him waving around, and some of there are poses that never showed up in the original training set. So this is beyond what other people can do. And as the depth cameras get better and less noisy, this is going to get even better. And what that means is that we're entering an era where people are, and this is much far beyond what the Leap does, because this is over a wide range of positions, and it's the full hand, it's not just fingertips. Means we're entering an era where when you put on your Oculus Rift or whatever, and you hold your hand up to your face, you'll be able to see your hand, and you'll be able to see yourself holding objects, and you'll be able to sort of enter a world that is a variation of your own world. So for those of you who work with 3D, this is like a big deal that we're moving in this direction. It also means that, for example, if I'm holding up an object, a physical object, and I'm looking at that object, I can say, hey, I'm looking at this object and it looks this big, I can make it look that big. So I can be holding a physical object and creating a virtual change to that object by visually changing my own hand together with the object to start doing things you could never do with video see-through augmented reality. Where actually this is the sort of steps toward that Werner Vinge world of we're changing the world around us. I'm having a conversation with you and working over a table together, and not only are you in California, I'm in New York, but you point over there, and we morph your hand to point over there because, to me, the map is a different size from you, and we just do that seamlessly. That's what we're trying to get to with this stuff. So this is, of course, what I want to get to, is I want to have these little, this is totally fake. I just basically took a picture of my own hand, and I drew a little critter that I wanted to see, like, wouldn't it be great if this little guy were looking up at you, right? Wouldn't that be awesome? So, you know, that's what I want to do, you know, once we get this thing done. So we started a project a number of years ago called iBird, and then apparently Apple took over the use of the word I at the beginning of anything. So they'll probably retroactively patent what we did, as they do. What's going on here is that this is called, there's a thing on the ceiling called a game track, which was this really cool game controller that we've now bought up all the ones we can on eBay because they're really neat, even though they got discontinued. Where you pull on this thing like this and you can flap your arms and pull like that. And he's looking at a screen, and these 3 fans, which are being controlled by computer control, are blowing vectors of air from different directions at him. And he's this bird, and he's flying through the air. So when the Oculus Rift came out, we realized, hey, we can do this in a much more immersive way now. We can track things with, you know, commercial consumer items like the Kinect. We can have people wear the Oculus. How many people have worn an Oculus Rift? So yes, you know what I'm talking about. You have a real sense of immersion. And we can still blow air on you. So this is Isabel, and she is wearing the Oculus, and she's actually pulling down on the Oculus Rift, which is, on the game track, which is mounted on the ceiling, and she's like being a bird and flying around. There's the 3 fans that are connected to Arduinos now, that you can actually see a picture of what a game track looks like right down there. It's like, I don't know, you pull on them. They're very cool. And having this experience, and actually I think we can see, this is what it's like to fly in this world. Zhu over there created this immersive world. And I guess Isabel helped a bit with it, right? Yeah. Procedural clouds with some sort of procedural noise function. And actually what I should show you also is what's really going on is that each of the 2 eyes of the Oculus, as you look around, and you can look around, of course you're seeing it distorted because it's really a wide-angle view, and so you're getting this complete immersion, and the clouds look like they're in the right stereo, etc. And so now we're setting up a world where people can then be together with each other and then see each other in this world, and that's kind of like where we want to go with this. Okay, so this is a program that the idea is to figure out, does that work? Yeah. Okay, good, I can make this. Hey, it's a purple crayon. So cool. All right, so what I'd like to do in the future, eventually, and we haven't completely implemented this, but these are some experiments, is I'd like to be able to do things like make simple shapes by just drawing them. And oh yeah, this is like, yeah, there you go. And then once I've drawn something, be able to then sort of interact with it, like as though it's a real object. And so that's the goal, is to be able to do that. And so the question for the research is, how far can we go in terms of this sort of like giving things, you know, explaining things, like I want to say like draw a simple shape. Actually, I can't. It's easier if I draw it with this. I think. Yes. There we go. And then, you know, and then make things come to life. Or if I want to draw something to show that, you know, I use that. And then maybe I can connect that to that. And then if I do that, there you go. So to give things sort of properties so that you have drawings that sort of have a kind of sort of lifelike properties about them, that's the goal of our latest research. Because we're doing all this stuff with tracking to try to create a sense of what's in the world, but we want to do the thing that you were talking about in your question, which is we want to give actual properties and behavior to the things we draw so they respond to us in real time.
I have a question.
Yeah, sure.
I recall that you were working on an animation program years ago that had to do with starting everything animation from the feet up.
Oh, right.
And I'm curious whatever happened to that, because conceptually I thought you were going to develop and allow people to use that.
Yeah, I'm going to actually get to some of that.
Oh, okay.
Right, that's good. Yeah. You're way ahead of me. It's amazing. So let me actually. For example, when I teach computer graphics, I find it's really awkward that I can't just like go up to a blackboard and draw something, and then the thing that I draw comes to life. So I want to be able to draw concepts, like if I want to teach about refraction or something, and be able to just draw some refraction and teach about Brewster's angle, and things like that, and then be able to say, oh, the thing that I drew actually starts having behavior after I draw it. Or if I want to explain to people about like, intersection of, let's say if I draw two circles, I draw another circle, and I want to explain about like how ray intersection works, then I should be able to sort of do things. And what I'm doing is I'm sort of communicating with the drawing program, which has some understanding of some of the things I could draw. And then as I draw them, it's like, oh, it's recognizing things that I draw. So, in the simplest case, I can do things like, I mean, this is kind of obvious, but it like knows that's, a letter, and then I could sort of, oops. I could sort of, let me actually, like for example, I'm going to be going to MIT. Oh, what happened here? Did something screw up? Hold on. So for example, I'm going to be going to MIT tomorrow, actually. I'm starting a semester sabbatical, and I'm all excited about it. So I did a little thing where I could like draw the word MIT and then look at the lab that I'm going to. So, oh my gosh, it disappeared. All right. Thanks. Let's start again. We're okay now because I think now we know what's going on. Is it showing up?
Yeah.
Okay. Just so you know, this is the first time I'm showing this software like to anybody, so it's like all these screw-ups are like, oh good, it's like something's working. I'm very, very happy about it. So yeah, so I was actually explaining about the MIT thing. I'm actually tomorrow morning, I'm taking the train to the MIT Media Lab where I'm going to be working with people there in the Tangible Media Lab, and so I just like sort of now, and I made it so that when I write the word MIT, it shows me the Tangible Media Lab. And I'm going to be actually working with, I'm working with a professor there, Hiroshi Ishii. So this is Hiroshi Ishii. Let's see if I can. Oops. I like Hiroshi, so this was my glyph for Hiroshi. And he's the person who directs the Tangible Media Lab. So it's very cool. Let me see if I can show you some other things. I also, Adam there is really interested in logic diagrams. So we built in a whole facility for logic diagrams. So for example, I can draw, this is a, I think this is a NOT gate. There you go. And then if I sort of draw a number 1, and I can then go, up and down, et cetera, et cetera. But if I click on it, I can link this to the logic gate. And then I can say, okay, what's the output? And because it's a NOT gate, it does this. However, NOT gates, as I learned from Jonathan, have delays. So I can then say, let's actually have a little delay circuit in there. So let me actually draw a little delay. Let's draw something that sort of controls something. And then I can control that. So now I have a half-second delay. So when I do this, it doesn't do it right away. But what's really cool about this is, for example, I can get rid of that, and I can move this over there, and then I can make a loop. And now, of course, it's actually running a simulation, so it's doing a negative feedback loop, and I can control the timing of the negative feedback loop with this. So it's really so I'm really interested in being able to explain things by just drawing them, but the drawings are smart and have semantics and have some of the ideas of a visual programming language. Let me show you another example that I really like. This is a very nerdy example. So forgive me for giving you a very nerdy example. Okay, cosine of x. Like those of us who had calculators when we were kids, the first thing you do is you keep saying cosine of x over and over again because it converges. How many people ever did that? Am I the only person who ever did that? Like cosine of x. So basically what I'm going to do is I'm going to sort of send cosine of x out to something. And of course, x, because I haven't defined it, it just defaults to 0. Is everybody with me? Mm-hmm. So cosine of 0 is 1. Cosine of 0 is 1. But now I can say, oh, let's feed that back in and call that x. And it just ran a simulator. And so now in real time, it just worked it out that when you say cosine of x is x, that's the x for cosine of x is x. Because everything's just running like crazy, and then it just ends up like settling on an answer. I don't know if this is making any sense.
This is like, reminds me of like Asian character entry on iPhones and...
Oh, so the interesting thing here isn't the character entry, because I can actually also...
but you're recognizing different things.
I mean, I can also just go and I can type. I can type the characters too. I can say, 1.5 times. So I'm just writing that because when I teach my class, I want to spell things out for them so that I can be talking while I do it. But I could just be typing. The problem is when I'm typing, you can't see what I'm doing.
Well,
so
what I'm suggesting is that from that inspiration, that technique of...
Yeah, sure. Yeah, I mean, basically, I wanted to make it so that if I wanted to write things out, like on a blackboard, I have the option to do it. But I can also just type. The problem with typing is it's less sort of directly visual to people I'm talking to.
So you have draw something you predefine in a dictionary.
Yeah, that's right. Like that. Exactly. Exactly. I just wrote a dictionary and I wrote a simple recognizer, and then I'm just looking at my own recognizer.
Excuse me. How do you think that helps learning? Because you're talking about all different kinds of visualizations. What does that do? Does it,
What happens then is somebody will ask me a question about something, about ray tracing or about logic diagrams or about something. If I draw it on the blackboard, I can't run it. If I can't execute it. I draw a cube. I can't show it from another perspective because it's on a blackboard. So it's just the chalk on a blackboard. If I just have a simulation that I've made beforehand, I can't say, someone asked me a question, let's use it as a real-time laboratory. So this lets me try to converge so that I'm gradually getting to a place where I have both together. The liveness of the blackboard and the smartness of the laboratory on the screen. So that's what I'm going for. But you're seeing very early work. But now, one of the things that I'd really like to do, obviously, is I'd like to be able to say, draw a character like the ones that you saw. And then now that, it's kind of boring if it's just a picture of a character, but we want it to, if it comes to life, it's more interesting. So we want like our drawing to come to life and then eventually to just, be able to sort of have behavior of its own. And so the next thing I'm going to be doing is developing a system where any character like that you draw, it recognizes it, starts importing behavior. And the stories that I told on the desktop that you saw, the 3 little birds of the love triangle, I can draw them, and I can even give them little smiley faces and little hints about what they're going to do. And then I'm actually just sketching out a story and some ideas, and they're responding to that. And that's where this stuff is going. And then eventually, when you and I are face-to-face in an augmented version of reality, and we have nothing but our bodies and our eyes and our hands and each other, then we'll be able to use these very, very simple techniques because we've understood the semantics of how I create something for you in real time and what I can author, because I have this library behind me that gives me a power-up, and I have things like Jonathan and Murphy's hand tracking to make it work really well. And then the shared virtual world we have between us becomes something that's actually not just a replication of our physical reality, but actually the kind of reality we'd really like to be in. And I think that's probably a good place to stop and ask questions. Okay, thank you.
Did you manually apply the motion algorithms to that, or did it recognize the feet and the head and apply it on?
What I did in this case was that I'm still working on the thing that lets it sort of know that that drawing is a bird. So I told it beforehand that I'm going to draw a bird. And once it knew it was a bird, it knows a lot of stuff about how a bird. I used all the stuff that he was referring to, all my procedural character animation stuff, like a bird can walk and its feet move and its body language and all that. So I was, and you saw that when the bird's running around on the desktop. So I was invoking algorithms that I use to make procedural characters and looking and walking and balancing and et cetera. And the next step that I'm going to do, and I haven't implemented it yet, but I want to show you guys this, is I'm going to make it so I can make a really rough drawing of anything that's vaguely like a bird. And it'll say, okay, I get that's a bird, and I'll bring that to life with those proportions and start moving it into the story. But I haven't implemented that part yet. Yeah. Hi, Gene.
How does someone who doesn't know you, but wants to use, and it's not a programmer, wants to use a bird thing?
So what's going on behind the scenes for all of this stuff is that there are layers of authoring. There are people who build libraries who are programmers. There are people who are, for example, would be high school teachers who teach math or teach physics who use those libraries. So the reason that we had two different screens is I'm actually, I have lots of help and hinting and explanations and online manual stuff on this screen. And it's actually really important that the teacher who may, they just downloaded a module about logic diagrams or about linear algebra over the internet, and they're using it, and they can be guided through, here are the things you might want to tell the students about next. Here's the blah, 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 here's that, or molecules, or whatever. So just as with PowerPoint, there's an asymmetry of view. The teacher gets to see all kinds of extra stuff to guide them through things. And then they can choose how much or how little the students see. But I don't think it can really work to give everybody a completely symmetric view when there is content that was created by other people that you have to absorb into the thing you're doing. I agree with that.
The teacher presumably could utilize tools that somebody else created, like verbs and things like that.
That's right.
Okay.
Yes, absolutely. I mean, this ideally is, if this is only a tool that I use, then that's failure. Eventually, the whole idea is to make a platform that you get a community of people, of programmers making some core stuff underneath, and then of people who build content on top of that. You don't have to be programmers who then start using their artistic judgment, arranging things, and then they make secondary content for other people. So you have a pyramid of content creation. Yeah?
I was just going to say, it almost feels like it could be more than a tool or interactive app, that it's like another paradigm of programming. The way that, something like MaxMSP or PD,
right,
these graphical environments, well, this is like another level above.
Right, and one of the things that Adam and I talk about in our research quite often is, yes, at the core level, somebody at a core level has built something in something like JavaScript.
Sure.
But then at some point, somebody says, oh, you have a module, it's a visual module. I'll put something that's like PD or whatever, and I want to put together a simulation that nobody thought of before. I'm not a traditional programmer, but I can do this. And then they make a custom physics lesson or something. So that we definitely want to be embedding there is the core Algol-like programming language, probably JavaScript, because that seems to be the world is working. And then above that, there can be the visual languages, which give you online hints and don't allow you to make syntax errors, et cetera. That can be used by people who have some sophistication, but they're not going to work at that level. And then they can be building, and then they can be publishing those mechanisms for other people to say, oh, great, somebody made this, but they were not a hardcore programmer, but they knew enough to use a visual language, and they know about physics or music or economics or whatever, and I can use their expertise. So we'd love to build that economy right now by building these things. And frankly, some of these things are absolutely real, at recognize, and some of these are fake, where I'm just like, I haven't figured out how to make a recognize for something yet. By building the look and feel and trying to understand this, we're trying to understand where we need to put effort in to build such an economy of sharing. So that's the question we're trying to ask. That's a good point. Yes?
So would the next step be building libraries that are a step down from the bird? Like, for instance, maybe building a library of just legs, so the system would know that when it recognizes legs, you could take legs and put it onto another object.
Absolutely, because you want to do people, you want to do dogs, you want to do elephants, and you want to basically, by the time you get up to a bird, you should be doing what he said. You should be snapping together components and maybe adding a little logic. You shouldn't be writing raw code at that point. I think you totally get it.
You want to bring it down to a real granular level if possible to really be able to, maybe a foot or a toe or whatever.
Right, and there are multiple levels of this. There are levels of recognizing what people draw and saying, okay, that corresponds to that, and then there are levels of putting them together and giving them behavior.
Sure.
So those two sort of efforts go together. Right. And then you start having something where no one ever thought of this before, but I'm just right in front of the class and I'm going to draw another ray in the ray tracer and let's see what happens and blah, blah, blah.
And a lot of this stuff is done in JavaScript and web.
What happened last August was I had been working entirely in Java for many years, like since the 90s. For those of you who remember the 90s, I had been working entirely in Java, and then last summer, two things happened. One is I realized that because there were these security problems, and I actually have a friend who works for Oracle who told me, yeah, Larry Ellison really doesn't care about client-side Java. Just my friend from Oracle said, just that ship has sailed, forget it. And then I went to SIGGRAPH. And I saw the most exciting thing I saw at SIGGRAPH were all the kids in their early 20s who were doing the shader toy stuff, were doing the the WebGL, and I was like, whoa, this is like what I was doing when I was doing this stuff years and years ago, except now it runs 1,000,000 times faster because people like me of my generation got people thinking about putting this stuff in hardware, and now a few $1 billion later, it's like, wow, it's 1,000,000 times faster. In fact, let me show you. Let me see, Firefox. The very first thing I made using a hardware shader was this. Oh damn, it's the same thing again. Hold on, let me mirror. Let me mirror so you can see what I see. Hold on. Arrangement, turn on mirroring, and now you'll see what I see. Okay, turn that off. Okay, so the very first thing I made was this, which is a procedural planet, and I knew how to make this thing like 30 years ago, but it took half an hour, and now it's running 60 frames a second, and that's the code, except for the noise function. So I could actually just make changes to this right here. I could say, oh, I want to change the star fields to be like streaks. And it goes down and it's reloading the fragment shader, and every pixel of this image, there's no actual geometry for those using this stuff. This is basically just a single square, and it's running a fragment shader. So even the planet itself is actually just a procedural texture. So I know some of you actually are not going to be interested in this, but some of you are going to think this is really cool, that I can just make any changes here. It's just in real time. I'm just changing algorithm. So once I realized that you could do this now, I haven't programmed at all in Java since August. I just taught myself JavaScript, I taught myself vector and shader programming, and I never looked back. And so all the stuff you're seeing now that I'm doing is entirely JavaScript, 100%.
Except for the projects like the bird you use in Unity or something like that? Rift? Or?
Well, oh no, that's right. Yeah, my students are still using Unity. That's right, they're using Unity. But for my personal projects like the chalkboard thing, that's all JavaScript. Yeah.
So you're going to HTML5 in Java?
You're accessing WebGL through JavaScript.
Well, yeah, this is WebGL. Okay. This example is WebGL. All the stuff that I showed you with the drawing, the chalk talk, was all just drawing to a canvas. It was just a 2D canvas. I wasn't even bothering with WebGL for that. So I didn't need WebGL for just drawing cute little line drawing stuff, So all those diagrams, yeah. So it all depends on what you want to do.
So at this point, I mean, aren't most of these libraries already kind of out there? Is it an issue of how do you make them accessible in terms of motion for physical forms like people?
Which libraries are you talking about?
Well, for example, like when you were showing the hand gestures that were being captured with the individual points, right? You're, I guess, aggregating a data stream that's coming out of that so that you can remap another image onto that.
Okay, well, you were talking about when Jonathan is fitting the 3D computer graphic model to the data, he's discovering where the points are. The problem there is that, yes, he and Murphy wrote an inverse kinematics algorithm to fit the hand model to where the discovered points are. The problem was that the data that's coming out of the depth sensor is noisy. And so what makes it hard isn't that, how do we make a hand? What makes it hard is how do we deal with noise and characterize the noise so that even in the presence of noise, we're still getting some kind of reliable pose. I mean, that's what's so exciting, and what they did is they're getting reliable they're getting hand gestures that are recognizable with incredibly noisy data. So if there were no noise, if this were purely in the world of synthesis and there were no actual real noisy depth data coming in, none of this would be hard, the stuff they're doing. It's just that they're doing heroic feats to deal with pretty bad sensors. Do I have that wrong? Yeah, I think, okay, good. Right, so that's why that particular work is interesting.
And for the stuff that you're drawing, you're saying, you know, you're making your own library of these, but...
Oh, well, making a graphics library, I'm just layering my own graphics library on top of the standard graphics library, so I have the convenience things that I want. Like, I have my own little IK function because it's the way I like to use IK. I mean, none of that's rocket science. I would say that the interesting thing what I'm doing is trying to figure out what's the deal between an author and a real-time user and a person who's seeing a presentation. It's not tricky algorithmic stuff. I mean, my character recognizer, you know, I did it in a day. You know, it wasn't
what is referring to? Maybe you want to do a Perlin.js project, like commonly used, like. You know,
well, actually, everything that I have here, I mean, you know, once I post it to the web, anybody, that's the beauty of JavaScript. It's all public. I can't hide anything.
You have to like reinvent the wheel again.
Right. Yeah. Actually, it's interesting because one of the grad students, actually Francisca, you know, one of the grad students came up to me in our lab, came up to me after seeing the little drawing and walking bird and all that stuff, and she said, "We really need to have a Git repository for our labs so that after you show me that, I can just go and download and play with it." You know, so I think, you know, there's something to be said for that, for people.
Go for an Oscar.
Yeah, what, say it again?
Like you said, you mentioned that you won an Oscar before.
Did I mention that?
In the class.
Oh.
Yeah, a long time ago.
Oh, okay.
So you can, maybe that can be initiated.
I guess so.
Like Perlin.js.
Perlin.js, there you go, Perlin.js. You heard it here first, folks. This might talk to my publicity manager. Yeah. Any other questions? Okay, yeah.
So there's a very famous vibraphone player by the name of Gary Burton, who learned that if he dragged a rubber mallet down a vibraphone, he could bend the note.
Cool.
And so he did all these recordings, but then everyone came to him, and all they wanted to do was bend notes. So he stopped doing that. So this is a prelude because I want to ask you about Perlin noise, which is maybe just a
Well, I am using it all over the place, but I use it like everybody else does.
Okay. And maybe that's like a footnote to everything.
Yeah.
But okay. I was curious if you could give us 2 levels of explanation for the mathematics behind that. One really high level, and then maybe just go 1 level down.
Yeah, okay. It's basically a kind of, let's see if this thing works. Does it work? Again, it's Java, so you never know. So basically, what Perlin noise is, from a high level, is it's a signal like this. It's what look like random bumps, but all the bumps are about the same size. And so think of when you look at a desert and you see sand dunes, or think of the way paint dries, and you know, you get all these sort of, the bumps look kind of random, but they're all about the same size. And the reason that it's useful is visual artists, you know, when you think back to what you do with a paintbrush, you pick a particular paintbrush with particular size bristles, very fine bristles or coarse bristles or whatever, and when you're painting, you're doing a statistical act. You don't know exactly where any bristle is, but you know the texture you'll get from picking that brush. So by scaling this thing to be bigger or smaller and mixing it in different ways, you can sort of get your texture brush. So because it doesn't bring its own flavor, it just brings a kind of controlled randomness, it becomes very easy for people to work with as a primitive, and then they can start putting together things like water or clouds or flame or marble or dirt or anything. It's the very boringness of it in a way, that it's the most boring possible, easiest to use possible, kind of random looking thing. But one of the things that makes it really useful is it doesn't just exist on a plane, it exists throughout all of space. So it's like you had sand dunes in a higher dimension. So every point in space, you see this sort of gloppy stuff is getting bigger value and smaller value. And that means that you can do things like, let me see if I can find some interesting examples here. Like, yeah, so let me see if I want to take a, I'm just moving noise past, I'm using this, by the way, because this is a water molecule. And as you can see, a water molecule, no corporation actually owns that image. So that's very convenient. But if you mixed 3 of them together, like if you mix notes of different frequencies, now you can see you're starting to get a more interesting texture. But all I'm doing is adding things of different sizes. And the fact that it exists through all of space makes it so easy to apply to things. You don't have to map it on. So that's the high level of what's useful about it. And then all of these are just like different examples of, this is like carving space out of it. You just like start using it as a carving tool or anything. And so the reason it got used in the special effects industry so much and so quickly was that, one, I just gave it away so that people could use it. And so here you want to make something that kind of looks like melting ice. So there I just use a little bit of this and it just sort of starts to look melted. It's very, very simple to use. And so did that explain it at that high level for you? Okay. So then at the low level, what's going on is that if you picture a piece of graph paper and you wanted to do this in 2 dimensions, then every point on every place where the 2 square lines intersect on the graph paper, you can pick some pseudo-random value and then fit some nice smooth like spline through it. Turns out not to be good enough because you can see that. So instead what you do is you tilt the paper. So at every place you actually have a pseudo-random little tilt of the paper and then you fit a curve between that. And that's how you would make noise in 2 dimensions. That's how you do it. And then the rest is details. In 3 dimensions, you got a 3-dimensional grid. Every XYZ place that's an integer, you tilt the value of the function in 3 dimensions, and then you fit a spline to that. And that's what noise is. That's how I implement it. And it's it's pretty simple. It's where is it? That's all the code. That's it. It's a very simple function. So if that sort of gives you a sense of it. And then you can just play with it, Here I'm moving it through a volume, so you see it's moving through the volume. And here I'm moving the volume itself, so it looks like it's actually stuck on the volume. And here I'm moving just the noise, but not the volume, so you see it actually exists through all of space. So it's just this thing that exists through all of space that you immerse something in, and you get this solid texture, like a bath of material that you're carving it out of. And that's why it's easy to use. So that's it, yeah. Yeah.
And you work with the Kinect. Did you, or are you aware of anything that's been done to sort of smooth out the noise coming from the sensor itself? Or?
Jonathan and I have a theory that maybe the Kinect 1 is better and maybe it isn't. You're battling with that right now. We got in the developer program, so we get to use the new time-of-flight one. The new time-of-flight one has really gorgeous silhouette edges, but it's got weird echoey effects, and the depth is kind of noisy, noisier in some ways than the old Kinect. The old Kinect was really bad, was that the edges were just awful, so it was hard to get silhouettes. And I don't know if you want to say anything about your current view of the new connector that doesn't involve curse words.
Yeah, and breaking NDAs. Yeah, I think people have tried cleaning up the silhouettes, especially because if you have a pretty clean RGB image, you might be able to do something better. Certainly at the level of like hands, everything's very noisy, but the biggest problem is probably just the lost pixels. So if you put your hand towards the Kinect, your fingers kind of just disappear from the depth image, and that's really hard to get back. The technique we use is a convolutional neural network. It can kind of do inference of trying to figure out from lost data where things might be, but it's a pretty tricky problem.
And you're saying that's something that wasn't happening with the first Kinect, that sort of...
Well, the new Kinects actually solved that problem. They're not using a structured light camera, they're using time-of-flight, but as Ken said, it has some other problems, so yeah, they traded some problems for other annoying problems.
And the problems with the first Kinect, you just lose really small things. Like if I can hold my finger up and it can sort of see it, but if I go like this, it's gone. There's no signal, which was really a problem if you're trying to do hand poses. Like you can't see this because there's nothing there. The new Kinect should be able to do that, but then you get other kinds of problems. And now we're battling with those problems, and hopefully it'll turn out that we can figure out how to work with the new Kinect and get a much more gorgeous signal. We're just still trying to wrestle it to the ground. We haven't quite gotten there yet. Yeah.
Going back to the picture you showed of the gumball machine on the corner.
Yes.
So talking more about augmented reality as opposed to virtual reality.
Okay.
Something like a Kinect or a similar technology, you have to be pretty much localized in a space as opposed to some kind of wearable like.
Oh yeah. Oh, but that's transitional.
I'm just wondering, have you guys done any work in that area?
Well, we don't need to do that because all the big companies are working on the tiny form factor version of the depth camera. It would be silly for us to do it because we already know it's being worked on. Because they all want to get it into the true wearable space. True wearable augmented reality. Like for example, Google Glass is not a true wearable augmented reality because it's not actually superimposing things on the real world.
Right.
But every single big company you can think of is working on it, and none of them will admit it. So there, I haven't mentioned any company because it's all of them. One of the things they're all doing is trying to make really, really, really small form factor, very low power components, including the depth camera. So yes, there are people working on that right now. They won't tell you they're doing it, but they are.
So a related question to that, do you think the tech industry has basically abandoned the idea of a physical pixel in space rather than a virtual superimposed image or like a visual stimuli?
I don't think it's abandoned. There are always people working on that. We did a project on that a number of years ago, and USC has done some interesting work. We did some things where we actually, illuminated dust in the air about 10 years ago, and we got some. But one of the problems with that is it's much harder to put it everywhere. It's the infrastructure problem. Then you need infrastructure. I do think that for economic reasons, as we have better power solutions and better, Moore's law, making the electronics smaller and cheaper and more portable, I do believe that technology is gradually just moving into our bodies. And eventually it'll just be inside of us, and we won't even think about it anymore. It'll just be like, getting dressed in the morning or not even getting dressed in the morning. So it's an economic thing. You can work on, what you think is going on with the Iron Man thing and maybe get something happening, but then Iron Man can only do that, Robert Downey Jr., Tony Stark can only do that there. He can't do that anywhere else except in his multi-billion-dollar lair. And then, the evil people who control the world in Hunger Games can only do it in that one stupid room. And so I think that's the problem, is no one knows how to make that ubiquitous and inexpensive. So that's why it's not as attractive a direction for people who want to throw huge amounts of money at making something that ultimately will be inexpensive and commercial and consumer level. Yeah.
So I got the Oculus Rift, and you put it on, and it's very cool. But there's a disconnect between what you're seeing and what you're feeling in your body. Going through a loop on a roller coaster, when you don't feel that, you get sick. And I don't see how, regardless of how much graphics processing power they throw at it, how many pixels they throw at it, how they're ever going to solve that.
There's an interesting project that I experienced about 4 years ago from Tokyo, where they do a little electrical stimulation to your inner ear, and they actually make you lose your balance, and you feel as though, and what's really creepy about it is, and it is creepy, is you have to sign this waiver before you use it, so you can't sue them later, is that they put something here and something here, and then they can basically steer you. So you're walking and they make you sort of walk to the left and walk to the right. And so it's possible that eventually, as the technology moves into us, it's also that whole sense of balance thing is also going to get affected. But I agree that every time there's a mismatch between two senses, you have potential cognitive dissonance. And that's always a problem with it's a problem with movies, it's a problem with TV, with everything we do. It's like it doesn't, why are those people 30 feet tall and flat? You just have to, deal with it. And sometimes it works and sometimes it doesn't. I agree with you. But yeah, there are people thinking about that. How do you do it?
It just seems like, you've got the Oculus Rift coming out, and the solution to that is nearer, but the solution to
I agree.
dissonance.
Well, and one of the reasons that we're doing the wind blowing thing is to try, like, well, how many cues do you need before you say, okay, something's happening? Like, what's enough? I mean, going back to movies and TVs, you think that you're seeing something here that has a nice dynamic range, but this doesn't have any dynamic range. You look around the room, the dynamic range of reality is vastly greater than the dynamic range of that. And there's a reason they make the room dark when you go to a movie. And if you actually put any scene from even the most vivid movie side by side with the most boring reality, reality blows it away. And yet, in our minds, we somehow do that mapping down to this narrow gamut from, quote, dark to, quote, light. And we believe we've seen reality because our brains can do that. So I think they're also hoping that they can fake you out by doing an artful combination of other cues, and you really feel as though, whoa. I mean, I know the first time I went through one of those ride films, you know, Star Tours, I was kind of genuinely surprised that I was back where I started. And I thought, what, shouldn't I be at the other side of Disneyland now, you know? And I realized they totally faked me out. They were rocking, and they made me think I was doing something else. So, and then my friend Josh, who had worked in that industry for a while, said it took them years to work out what fake things to do that would fake you out. Or what the first things they tried didn't work. So it's not hopeless. It's more like now they can start, now that we have the Oculus Rift, now it's an interesting problem. It becomes an interesting problem because now there's a consumer market. Yeah.
I'm just wondering, seeing that you've worked with the Kinect too, if you noticed a community springing up around it, because I've been starting with it as well, and it seems like crickets compared to the original.
Well, the original Kinect, Johnny Lee offered that, what, $10,000 or something, for whoever could hack it first. You know, totally subverted his Microsoft KGB masters. And then Microsoft said, of course we meant that all the time. We wanted everyone to play with it. I'm sure that was true. And so you had this vast community of hackers immediately, within a week, who were playing with the original Kinect. For us, we had to sign NDAs, we had to do all this stuff to be in the developer program, we had to be chosen. They're keeping a very tight control. They're not creating a community of PC developers around the Kinect 2 yet. They may eventually, but since there's no community that's of any significant size, these sorts of happy accidents really aren't going to happen yet. Once you have tens of thousands of people who are just hacking away at it, then you're going to start seeing something different. But if it's just a few of us researchers, you know, we'll publish them. I think Microsoft likes to move slowly. That's,
new CEOs.
well, there you go. Yeah.
You've been talking about this world that's inside the head, not out there on TV.
It's a world I live in every day.
Right, yeah. But in terms of comparing it to the technology we have right now, and we have this model of communally watching things out there.
Yes.
And we watch real world, well, what we think of as real world out there. You're talking about CG in here.
Well, it's interesting. I mean, you know, when you see a movie like Gravity, what do you think you saw? Do you think it was all CG? I mean, at some point, the two start crossing each other. I mean, there isn't any actor in Hollywood who actually looks the way you think they look. You know?
Right, but what if you want us to share the real world?
I mean, I think that the most interesting uses of these sorts of things are when it's ordinary, when it's everyday. You and I are talking, but there's something right here that we both want to look at, and we want to refer to it now, and we want to be able to look at each other and not like, oh, I'm watching my little screen here. I think we're going through this weird temporary thing where everybody's staring down at these rectangles. And I think it can't stay that way. It's sort of not natural for people. So I'm hoping for a world where we're having this conversation and you want to bring something in, but we're still having our conversation. And you want to join the conversation. And I firmly believe that the good scenario, which we can get to if we focus on it, is the heads up, it's just us people again. And then we have our stuff when we need it. But it doesn't replace eye contact and body language and all the stuff we're really good at. I mean, there's a big portion of our brains that's really just devoted to eye contact, body language, facial nuance, proprioception, all this stuff. And right now, with the you know, Steve Jobs magic rectangles with the rounded corners, we're sort of kind of not using all of that temporarily, and it has to end because it's not what our brains are good at.
Well, I was thinking about it also in the context of like Michael Bova at MIT is working with holographic TV.
Right.
He's using Kinect also
Right.
for interfacing. And I mean, how do you see that in relation to what you're doing? Do you fit?
Well, I mean, I don't know. I mean, TV is TV. I think TV.
Do you think TV will go away?
No, I mean, I think. I mean, that's a complicated question. Do I think? I don't know. If I think books won't go away. I don't know what they're going to look like, but people will still tell stories with protagonists about journeys of people who don't really exist but represent the human condition. I don't think that's going anywhere ever, because that's what we all want. But what medium we use, I mean, the TV didn't replace movies. Movies didn't replace novels. Nothing replaced theater. They're all sort of coexisting, sort of in some sense the same medium. Game is a different medium, because game isn't about protagonist-driven narrative. So in some sense, I don't even know that that when you're talking about storytelling, the physical medium is even the most interesting part of it. I think the storytelling is the most interesting part of it. And anything that supports me being able to tell you a story, a great theater director or a great film director or a great novelist has their own tricks for their medium to tell you a great story. New media will just have new tricks for telling a great story, and that's fine. But I don't think it's essential when it comes to something like I'm watching something on TV. It's not the important question for that, in my opinion. Sorry, I got all literary. Anybody else?
What kind of stuff are you working on with WebGL right now?
Well, you saw the stuff with the planet. I made my students this fall semester do all their projects in WebGL, and some of them did just amazing things. So I used WebGL all through the fall semester for my graphics class, and then I took a break from it so I could build this drawing tool. And then what I'm going to do sometime the next month or two is bring the WebGL back into the drawing tool so that you can make drawings that then trigger full three-dimensionally rendered things, because then that's going to feed back not only in how I teach my graphics class, but also into our virtual reality stuff. So that's my personal plan over the next few months. Yeah.
You keep talking about how you want to have this world where everyone's in the same sort of virtual space, but none of the projects you showed us really talked about the networking aspects of it. I'm just wondering if you or any of your students have done that, especially now with the WebGL capabilities.
Well, one of the things that Adam and I are wrestling with right now is the question of how do you build the community and what kinds of communities. For example, if this is pedagogical, then I give an inspiring lecture in class, and then the students, who may actually be following me over the web, and what I'm drawing is puppeteering their web browsers, then they get a sandbox where they get to play with this thing themselves. They make their own logic diagrams, and then where do they publish that, and how do we assess how they did and what they're learning? And all of those are questions about how you share and what you share and what's the persistence. So once we get this stuff to a point where it's good enough to start testing out in a community, there'll be a lot of interesting questions about what the persistent models are and what the publishing models are, and how do people add to a commons without breaking everything. Those are really important questions. I feel as though they're going to dominate our thinking sometime half a year from now. But right now, we're just starting to build those pipes. Yeah.
Your students are coming in with a different visual language than you grew up with. How does that change your direction of your work? I mean, you have a certain basis of experience. They have a different basis of experience. Has that altered your direction of how you do things or how you see things or where your goals are?
I don't think that turns out to be the crucial thing in a computer science graduate program, in my experience. I think the thing that turns out to be a crucial thing in the computer science graduate program is that I use tools that they find relevant. So they're very happy that I'm using the WebGL stuff because they feel that that's relevant to them. But questions of visual language and differences of visual language across generations, I think, are more pronounced in other disciplines. But I don't think it's not the thing that holds us back in a computer science community.
Okay, I think we're pretty much at time.
Okay. All right, thank you.
Thank you.